Hi everyone, I'm Chaoyi Ruan from National University of Singapore. I'll talk about the Cortex, a semantic cache for LLM agents that spend most of time in data accessing. By caching a tool called resource semantically, Cortex can make agents faster and cheap. This is a joint work with collaborators with University of Toronto and the USTC. I will cover 4 things. First, I will talk about why agents are bottleneck on remote data, and second is the Cortex design. Finally, I will introduce the evaluation and wrap up today's talk. So what does agent actually do? The diagram on left shows the loop. Usually it consists of 3 steps. M decides which tool to call. This is the thinking step. Then the call goes out over a network or call a tool. That's the very latency height. The response of tools feeds back into a context, and then the cycle repeats again and again, sometimes a dozen of times until the agent emits final answers back to users. Every tool call actually is involves some network operations and some remote data service sitting in the critical path. Next, let's see the loop in action. The same architecture, but I use an example to illustrate. A user asks a single question, say who paints the Mona Lisa, and the agent will issue a search call, maybe Google Search API, something like that, to a remote data service, get results and resume the generation. A typical multi-hop questions file 4 to 6 of these codes in series. Each mode, each one is a remote round trip. Now we know what loop looks like. Let's see what's actually caused. In typical search agent like search R1, the GPU sits idle in around 40 to 50% of work clock time, just waiting for the data. In other words, you are paying 1.49 per each 100 hours to do nothing. Less data fetches from itself costs real money. $5 per 1,000 of requests for Google, and $25 per 1,000 for OpenAI's web search API. On top of that, heart rate limits keeps throughput regardless how much GPU storage. For example, like Google Search API usually will impose 1 request per minute for each single user using API. So bottleneck sometimes isn't just a GPU computer. Of course, GPU computing is still a bottleneck, but it's not the only compute. Sometimes data will become another new bottleneck. So the never follow-up question is, can we cache it? Yes. Here, to evaluate whether if we can cache it, we put a Google search trace. Currently Google has already integrated AI into AI mode, proposed AI mode in their workflow. So we put a Google search trace and look at the query rank versus what the top queries gets roughly 10 times of the value of rank 5. Let's suppose where you look at 24 hours on 7-day window. The tail is very long, but this tail entry is very repeated. In other words, a small cache covers most of traffic. It's a special argument for caching. Now let's look at some temporal arguments. Then Google trained data, but view over time. Sparks are sharp. For example, on GPT-5 launch, they also correlate to many users at once, searching for OpenAI. The other example is Ellipse second and Charles third. Both had heavy distribution and burst make agentic workloads cache friendly. They have correlations, they have bursty patterns, something like that. So cache is on the table. But the next question is, what kind of cache do we really need? We summarize 4 requirements derived from how agents actually behave. Start from tab left. Agent queries are paraphrased in natural languages instead of the traditional key-based. They are not byte identical. So cache needs some semantic match instead of the key exact matches. Now the top right is a cache web 7 seconds, while a data lookup 7 milliseconds. Evasion also need to factor in the vehicles, not just the frequency, because data retrieval requests may be different. Some data will be, retrieval cost will be very high. I will explain later. Now the bottom left is agent fetch from the many providers across regions, so cache must be distributable. And the bottom right, the external APIs throttle sometimes will throttle users' requests. So the cache needed to absorb, burst, and stay under quotes. Currently, no existing systems cover all of 4 systems. This table works through 3 families against 4 axes. Usually, currently in LLM's era, the most popular cache is key value cache. However, it's cache token state. It's about how to accelerate LLM inference itself instead of the external tool calls. Also, they cannot solve the cost and cost region really limits the properties of agentic task. The second one is problem cache. The problem cache means GPT cache. For example, the most popular example is the GPT cache. It's used the AI embedding to compare similarity between the current query with the previous historical queries. If this query is very similar to the historical queries, it will immediately return results of the previous one back to users. However, sometimes they will return wrong answers. This is because text similarity doesn't always mean the semantic similarities. Very simple example, tell me 1 joke and tell me 2 jokes. They are not the same thing, refer to the same thing. The third one is very traditional, like a traditional cache, like key value cache. Like Redis, LocksDB, something like that. Usually, they will maintain in-memory cache to avoid some SSD accessing tests. However, as we discussed before, those traditional cache they focus on the exactly match, because usually this cache follows key value models. They will do some byte identical comparison to locate cache items. So to solve these questions, we propose Cortex. Now let me show you the design of Cortex one by one. First, I want to clarify what we are aiming for. Today's every tool call goes remote, slow, and expensive. We want semantically similar queries to hit a local cache instead. The question is how. Let's start with strawman solutions. The obvious looking answer is the approximate nearest neighbor search. You use the AI index to index the similar data. For example, embedding each query into a vector, index millions of entries with AI index like HNSW or something like that, return a top K cost by cosine similarity in around the millisecond time scale. If a stored query is close enough, say the similarity above, for example, 0.95, something like that, just reuse its cache answer. This design sounds very clean and fast. However, it breaks in 3 ways. The first point we have alluded before is similarity isn't equivalent to the semantic. For example, this is another example, like the OpenAI founder and the OpenAI CEO. They share a lot of common words. In some embedded models, their similarity is very high. However, they are not refer to the same thing. The second point is loss cost aware. AI index is not equivalent to the cache. Cache has capacity. It needs to decide which item should be evicted. We cannot assume the cache has an unlimited size. So the question is, however, if we just evict items based on frequency, sometimes, for example, sometimes one item will be evicted even though its retrieval cost is very high. So this time we need to factor in other factors apart from frequency. The second point is freshness. Even though the queries are semantically the same, however, we need to think about the data freshness because information has its left hand, for example, the stock price changes every day, and the value also changes. Stock price changes every few seconds, and the value, like what's the value? This question's answer changes every day. So we need to consider the staleness. So based on above this Stallman solution, we introduce several fixes to make it a real semantic cache. The fixed one is the key value unit itself. Here, we propose our first instruction, a semantic element. It wraps up the query response and 5 metadata fields: cost, statistic, frequency, size, and latency. With this metadata, each entry becomes independently rankable and comparable. For his decision, eviction policy, a prefetch candidate. That's what makes our design decision possible. The fix 2 is a retrieval pipeline. Here, based on this, we introduce our theory index. Theory has 3 stages. First is a regular AN retrieval process. We call it a cost field. Vector similarity above a given threshold will be returned. So after the first cost field, we will get a smaller candidate set. After that, we will introduce LLM as a judge. Because we imagine doing our work, we imagine find that currently small LLMs has had a lot of capabilities to do some very simple tasks. For example, ranking, and do some for some binary tasks or some classification tasks. They are very good at such tasks. So we use the Queen 3.5 we use the Queen ranking model 0.6 billion to do such judges because LLM can really understand the meaning of the sentence. The third is recalibration. We will dynamically recalibration the stage 1 threshold and stage 2 threshold. The work dynamically tune it. Okay, now is about the cache policies built of The first is straightforward. A hit only counts after full AN as judge pipeline confirms it. No premature results from a similarity will be returned. For eviction, we design a customer policy called LCFU. Each item gets a score combines of frequency, cost, latency, and statistic divided by size. In practice, expensive frequently accessed and so changing items stay in the cache. Cheap, rare, and ephemeral ones get evaluated first. Also, we introduce some prefetch mechanisms, lightweight Markov models to predict the next likely items based on the current queries. It will easy to warm up cache and avoid some bursty requests, something like that. Okay, the last is about some architecture design. As we introduced before, we leverage a small LLM as a help. However, we cannot. However, for example, the regular VLM will occupy entire GPU for each model. Here we leverage some CUDA multiple MPS mechanisms to make these two models share in one GPUs. However, we introduce some mechanisms to give high priority for agentic models, and we avoid the judge models to affecting the agentic models. So we can use one GPUs for serving two models. Oh, okay. Now you have seen that each pieces the data client inside the tool calls theory checks cache with our theory indexes. Eviction and prefetching run in background, driven by metadata you saw earlier. The judge shares the same GPU as agent. That's the full system. Now let's see how it performs. We use some popular open source search agent, which is post-trained on top of Queen 2.57 billion, Queen 3.8 billion, something like that. We use H1 class, a GPU cluster as a search, and with real Google search APIs. We use hot polyQA, mostly wiki, some data set. We test two baselines. One is the VLM without our cache. The other one is the VLM with exact cache. We measure throughput and latency. Here is our primary result. Across all benchmarks, we achieve nearly about 3.6 times throughput on MuseQueen data set, same trend across Xinyi GPT data set, pod QA and a wiki dataset. We also maintain a very good hit rate and significantly reduce the latency. We also our own LCFU cache policy eviction also adapts to very good a bursty Google trend, achieve nearly a 95% hit rate and a 3.8 throughput boost. And also we measure our accuracy. If we use AI only, it will lose 10 point accuracy in dataset. With our cache, we can maintain accuracy. Also bring some improve cost efficiency by up to 6 times. This is mostly because we can save GPU resources for judge models, and also we naturally can avoid the rate limit relief because we can use the local cache result instead of accessing remote data each time. Okay, let's wrap up today's talk. I hope 2 points are taken back home. One is in this era, agentic becomes popular. GPU is of course is still a bottleneck, but ours factor becomes a new bottleneck. Maybe like a CPU on data, it needs more works to solve this problem. The second point is due to agent becomes a very software application, we need to rethink the traditional common sense, like cache. Maybe we need to think about how to integrate the LLM capability to the traditional software and innovate it. Thanks, everyone. I have finished today's talk. I'm happy to take any questions.